Our universe is vast, an almost incomprehensible expanse that stretches beyond the limits of our imagination. It's filled with billions of galaxies, each teeming with stars and planets, each a potential cradle for life and mystery. But what if this isn't all there is? What if the universe we know is just a small part of a much larger, more complex reality? What if our universe is just one of many, coexisting like bubbles in a cosmic foam, each bubble a separate universe with its own unique properties and laws? This is the mind-boggling concept of the multiverse, a realm where infinite possibilities unfold across a tapestry of parallel universes, each one potentially different from the next. For centuries we've gazed at the stars and wondered about our place in the cosmos. We've asked questions about our origins, our future, and the nature of the universe itself. Now cutting-edge physics and cosmology are pushing us to expand our vision even further, challenging us to think beyond the confines of our own universe. The multiverse is no longer just the stuff of science fiction, it's a serious scientific hypothesis, explored by physicists and cosmologists worldwide. These scientists are developing theories and conducting experiments to test the boundaries of our understanding. The idea of multiple universes challenges our understanding of reality. It forces us to reconsider what we know about the cosmos and our place within it. It suggests that the laws of physics, the very fabric of existence, might be different in other universes. Imagine a universe where gravity is stronger, or where the speed of light is different. This opens up a dizzying array of possibilities, from universes where gravity is weak, to universes where time flows backward. Each universe could have its own unique set of physical laws and constants. While the concept of the multiverse is still highly theoretical, it has profound implications for our understanding of the cosmos and our place within it. It challenges us to think beyond the familiar and to consider the extraordinary. Let's delve into the science behind this captivating idea and explore the potential evidence that suggests we might be part of something much grander than we ever imagined. The journey to understanding the multiverse is just beginning, and it promises to be one of the most exciting scientific adventures of our time. One of the most compelling theories suggesting the existence of a multiverse is the theory of cosmic inflation. This theory, first proposed in the early 1980s by physicist Alan Guth, has revolutionized our understanding of the early universe and its rapid expansion. This theory proposes that our universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. During this incredibly brief moment, the universe expanded faster than the speed of light, growing from a subatomic size to a macroscopic scale in an instant. This rapid expansion, known as inflation, stretched the fabric of space-time, smoothing out its wrinkles and creating the uniform universe we observe today. The process of inflation also helps to explain why the universe appears so homogeneous and isotropic on large scales, despite the chaotic conditions of its birth. But what if inflation didn't happen just once? What if this extraordinary event is not a singular occurrence but a continuous process that has been happening throughout the cosmos? What if it's a continuous process, constantly giving birth to new universes? This idea leads us to the fascinating concept of eternal inflation, where inflation never completely stops and new pocket universes are constantly being formed. This is the idea behind the bubble universe theory. In this scenario, our universe is just one of countless bubbles that have formed in a vast, inflating multiverse. Imagine a pot of boiling water with bubbles constantly forming and expanding. Each bubble in the boiling water represents a separate universe, each with its own unique properties and characteristics. In this analogy, each bubble represents a separate universe, expanding into existence within the vast cosmic foam. The space between these bubbles continues to inflate, pushing them apart and creating more room for new bubbles to form. According to this theory, our universe is just one bubble in an infinite sea of bubble universes. Each of these bubble universes could have different physical laws, constants, and even different dimensions. Each bubble universe would have its own unique set of physical laws and constants, potentially leading to vastly different cosmic landscapes. Some might have stars and galaxies similar to our own, while others could be entirely alien with forms of matter and energy we can scarcely imagine. Some universes might be dominated by black holes, while others could be filled with exotic forms of matter and energy. The diversity of these bubble universes is limited only by the imagination and the underlying principles of physics. The bubble universe theory is a captivating concept offering a glimpse into a realm where the possibilities are truly endless. It challenges our understanding of reality and opens up new avenues for scientific exploration and philosophical inquiry. However, like all theories about the multiverse, it remains highly speculative. The idea of multiple universes existing simultaneously is a profound and complex notion that stretches the limits of our current scientific knowledge. We lack the observational tools to directly observe these other universes, making it challenging to test the validity of this intriguing idea. Despite this, the theory of cosmic inflation and the possibility of a multiverse continue to inspire scientists and fuel the quest to understand the true nature of our universe. String theory, one of the leading candidates for a theory of everything, offers another possible pathway to the multiverse. This theory attempts to unify all forces of nature by proposing that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. String theory requires the existence of extra-spatial dimensions beyond the three we experience in our everyday lives. These extra dimensions are thought to be curled up or compactified, too small to be detected by current technology. However, their geometry and configuration could have profound implications for the nature of reality. One intriguing idea that emerges from string theory is the concept of brane worlds or membranes. In this scenario, our universe exists on a three-dimensional membrane or brane floating within a higher dimensional space. Other branes representing other universes could exist parallel to ours, separated by an unfathomable gulf in these extra dimensions. Collisions between these branes could potentially release enormous amounts of energy, potentially leaving observable imprints on the cosmic microwave background radiation, the faint afterglow of the Big Bang. Detecting such signatures would provide tantalizing evidence for the existence of these hidden dimensions and the other universes they might contain. Quantum mechanics, the theory that governs the behavior of matter and energy at the atomic and subatomic levels, is notorious for its bizarre and counterintuitive predictions. It challenges our classical understanding of the universe, presenting a reality that is both fascinating and perplexing. The principles of quantum mechanics have been tested and verified through numerous experiments, yet they continue to baffle even the most brilliant minds. One of its most mind-bending interpretations, the many worlds interpretation, suggests that every quantum measurement or event causes the universe to split into multiple parallel universes. This idea, proposed by physicist Hugh Everett in 1957, implies that all possible outcomes of a quantum event actually occur, each in its own separate universe. Imagine you flip a coin. The simple act of flipping a coin can serve as a metaphor for understanding this concept. In the classical world, the coin will land on either heads or tails. This is a straightforward, binary outcome that we can easily grasp. However, in the quantum realm, both possibilities exist simultaneously until the moment of measurement. This phenomenon is known as superposition, where a quantum system can be in multiple states at once. According to the many worlds interpretation, at the moment you observe the coin, the universe splits into two parallel realities, one where the coin landed on heads and another where it landed on tails. Each of these realities is as real as the other, but they exist independently and do not interact. This process of splitting occurs constantly, with every quantum event spawning a multitude of new universes, each representing a different possible outcome. The sheer number of these universes is beyond human comprehension, creating an ever-expanding multiverse. In this view, the multiverse is not a collection of distant bubble universes but rather a vast, ever-branching tree of parallel realities. Each branch represents a different sequence of events, leading to an infinite number of possible worlds. While the many worlds interpretation is a fascinating concept, it remains highly controversial within the scientific community. Some scientists embrace it as a logical extension of quantum mechanics, while others criticize it for its lack of empirical evidence. It lacks experimental verification, and some physicists argue that it raises more questions than it answers. The interpretation challenges our understanding of reality and forces us to reconsider the nature of existence itself. Nonetheless, it highlights the profound strangeness of the quantum world and the potential for reality to be far more complex than we can currently comprehend. The many worlds interpretation invites us to explore the boundaries of our knowledge and to imagine a universe filled with endless possibilities. If you enjoyed this exploration of the multiverse, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss an update. Thank you for watching.